Hello friends, so let's continue with the third and final part of this simulation of direct torque control of induction motor. So we have learned in theory how the direct torque control works, and for last two videos I am trying to explain how to do it, how to simulate the direct torque control of induction motor drive in Matlab, right? So in this third part, I'm going to show you how to set various parameters or other tuning of DCT on DTC controller. So let's continue with the video of third part, that is tuning of DTC control. So major questions while setting up the simulation of DTC which one faces are what should be the flux reference value? What should be the width of hysteresis bend controller? What should be the width of flux hysteresis bend controller? What should be the limit of P star for large error in speed? What should be the sampling period? What should be the KP and KI? So these are few major questions. There are many small and trivial questions which we cannot cover over here. But the major parameters which affect the performance of the simulation are listed over here. So let's try to understand each question one by one, and then we'll see it in the actual simulation also. So first is, what should be the flux reference? Now in induction motor, flux is to be kept constant. Flux is changed only when you want to go speed beyond the rated speed, that is in a flux weakening region. So if flux is constant, that means whatever rated flux is there, rated stator flux is there, that is been given somewhere in the specification. So either find out from that. Now the preset model which I have used in case of Matlab, it does not have the flux reference. So what I did was I had one option is that I can calculate using fundamental formula, but I use a simple approach. I run that induction motor with the rated voltage with all rated parameters. So when there are measurements possible in the signaling itself. So I ran the motor, I simulated the motor with full direct online rated voltage. And then when it was in steady state, I measured what is the stator flux. And that is going to be the rated flux, because with rated voltage and rated frequency, motor is supposed to produce rated flux, right? So that's the concept, that was the way I did it. So now let's go to the next question. Next question is, what could be the width of torque hysteresis bend controller? Now we want that this torque should be equal to rated torque, equal to whatever is the required torque. It is actually in steady state, it is equal to the load torque. So variation in torque, that is you can say torque pulsation should be minimum, and this torque pulsation or you can say variation in torque is because of the width of hysteresis band, right? So the logic is that how much should be the percentage allowable torque ripple. Now this torque ripple affects the load. So based on the load requirement, percentage torque ripple allowed is suppose available. Based on that, we can select the width. I'll show you in the simulation how to adjust it. Now narrow width for less torque ripple, but it leads to large switching frequency, because if width is zero, quite frequently it is going to switch. So that is something which should be possible for us to accommodate such a large switching frequency. So that is the limit. If we keep wide width, then the switching frequency is going to be within limit, no issue with that. But then the torque ripple is going to be very, very high. So choice is a compromise between allowable torque ripples and limit of maximum permissible switching frequency of the power electronic device. Right? So that is something which you can try with different permutation combination and see what is the effect. Right. The third question is, what should be the width of his flux hysteresis band? So the flux hysteresis band affects the stator current. So stator current distortion will be based on how much is the width. I will show in the simulation also. So we have to keep it minimum so that the stator current is having very less distortion. Right. So narrow width for less distortion, but then once again for that, the switching has to be very frequent. So switching frequency will be very high. It may happen that our power electronic device which we have used, generally IGBT, will be the device which will be used. So it may not support it. So in that case, it's not possible. And wide width, if we keep, then the stator current is supposed we will have distortion. We'll see it in simulation also. The choice is a compromise between allowable distortion in stator current and limit of maximum permissible switching frequency of the power electronics device. What should be the limit of the TE star? There is command torque. Now the TE star or command torque is the torque at which this is the torque at any sampling period motor should produce. Our required torque. And required torque is not directly given, though it is a direct torque control. We generally in a speed control loop, we indirectly generate the required torque based on our speed error, right? So let's see how this topic is handled. So for large positive error in speed, that is actual speed, reference speed minus actual speed. The large positive error indicates actual speed is less. That means we need to increase the speed, and we can increase the speed by increasing the by producing more torque. So for that, the limiter now who sets this more torque? So there is a PI controller, and it is followed by a limiter block. So that saturation or limiter block is having upper and lower limit. So you select upper lower is the maximum torque or the TE star at which you would like to accelerate, and lower limit is again same value but in a negative value, right? So TE star limit can be set to Tmax. We can have a twice the rated torque. We can have 1.5 the rated torque. It depends on at what how you would like to accelerate, right? So it can be now. If you don't know what is Tmax, then you need to calculate, and then at first that you can set the limit. So good dynamic response, it is found in most of the drives. The acceleration and deceleration is at maximum torque. You would not like to cross it. Now next question is, what should be the sampling period? Now sampling period is very tricky. Of course, for a good simulation, for a very smooth curve, the sampling should be very fast, or sampling period should be very small. So you would like to keep it say 1 microsecond or 2 microseconds. But is it possible that all different measurement of voltages and current, then all different calculation of stator flux, torque from all those measurements, is it possible in the real time to complete these estimation or calculation within 1 second, say microsecond? If yes, then only I can keep 1 microsecond as sampling interval. So within the sampling interval, all these different changes or you can say estimations must complete. So it depends on the complexity of the estimation of the various parameters from measured values and current. So we also need a very fast processor if the complex calculations are there. Of course, we have a measurement, so you have analog to digital converters and all. So you have their conversion time also affecting. So all these are taking contributing, and based on that you select sampling period. Sampling period should be large enough within which all calculation estimations are completed. It also depends on the processor speed, maximum possible switching frequency of power electronic switch, etc. Here in simulation, in Matlab simulation, it is a numerical number, so it is all right. But in reality, when you want to have a real-time simulation, the sampling period will be limited, or it will be having constraints with all these parameters. So here we have simulated with 20 microsecond. I'll show you simulation with different values and see its effect, right? It's a big subject. The simulation which we are discussing, it's a crude simulation. I am not hereby claiming that this is a perfect simulation. This is a beginner simulation. A lot of tuning, lot of work can be done. I'll be sharing the simulating file also with you. So we are all learner or students of this subject. All are there to improve it. So there are many aspects in which we can improve, but the basic draft, a skeleton of which I have prepared and I'm sharing with the students so that they can work on it. They can learn new things and they can share with the world as I'm doing, right? So this simulation is not the perfect one. It is not the complete one. It is the beginner simulation where a lot of tuning is required. I may have made a lot of mistakes also, which you can point out in your comment section so that people also learn from it. I also learn from it and I try to incorporate all the changes, and maybe in future I'll have an improved simulation once again shared with you. And the last question which we are going to discuss is what should be the value of KP/KI. So KP and KI are to be adjusted. These are the gains of the proportional or integrator or PI controller. Now, generally, the objective of this adjustment is to get the best possible steady state or transient performance. Now, what do you mean by transient performance? That quickly the speed should rise to whatever is the steady state speed. So rise time should be small, no overshoot, and KP should be basically targeted towards the reducing the steady state error to say possible if possible 0, or otherwise it should be minimum, right? So once again, a lot of work can be done in PI tuning itself. So I have done over here a simple trial and error method over here. A lot of work is still pending, and students are encouraged to go for a very proper method of PI tuning, and then you'll have a better performance. So here, by trial and error, I have tried to limit the error within say 2 to 2.5% range, and then that's all which I'm going to show, that how KP and KI, by changing how the steady state error or the rise time is affected, right? So all these different control system related study also you can do with this simulation also, right? So that's all the questions. Now let's see the demo and these questions. We'll start with the first question. What was that? Yeah, flux reference. So we'll start with that. So now this is the simulation. So here you can see that this is the induction motor or asynchronous motor, and this is a bus selector. I am using in this version. This bus selector is offering me all these parameters. So stator measurements, I have stator current Q and D values, stator flux Q and D values, speed and torque. Speed and torque I am measuring. Torque and flux I am calculating also. So all these parameters are passed to DTC controller. In DTC controller, you can see this flux reference is given to the flux controller over here. You can see this flux controller is having phi S reference, and what is the value? Its value is 0.7. And in simulation, we can see we have achieved that or not. So let's simulate this. Yeah. So let's simulate. Compiling. Let's see whether we are able to achieve. So just concentrate on the flux part in the waveform. Same way, all other different parameters also I'm going to show. So you look at this simulation and you can see that it is 0.7. This is the flux. The third column from third waveform from the top is flux, stator flux magnitude, and you can see it is 0.7. Right? So it is pulsating within this band. So 0.7 is what we have achieved, and we are maintaining it constant throughout this simulation, which you can see over here. Right? So that was first. Now, second question is what should be the width of the hysteresis band? So you can see This is torque controller, and the hysteresis bandwidth is decided by this gain. So here I have kept it 0.05. That is, whenever the error between actual torque and estimated torque is say higher than 5%, I have considered it as a large positive error. For this, +1 will be set. It is, if it is less than 5%, so it is large negative error, so -1 will be set, and within that band it will be considered as a 0. So likewise, the status signal should be produced, right? So you can change this this 0.05 to a smaller or larger value and see the effect, right? Similarly, flux hysteresis band I have set over here. It is this component in which I have kept it with the upper and lower limits. So with that, this I have kept to be 1.5, 1.5, 0.015. So 1.5% on plus side, 1.5% on the bottom side. So 3% variation I am allowing, right? You can change with the different bits. Then the limit, the torque limit, you can see this is what I am at present kept it to be rated torque itself, because applied, I have not applied, I have applied only 25% of the load. So it is all right that I would like to accelerate at the rated torque, but I can go at the maximum torque also if I want to run the simulation at full load, right? Here the applied load is only 25%. That's why I'm marking this PE star. This is upper limit 800 Newton meter, which is the rated torque for it, and -800 is the if speed is reduced, right? So this is it. Simple sampling period you already know. This is 20 microseconds is what is set over here. I have a simulation type discrete, and the sampling period is 20 microseconds. PID tuning, if you talk about, it is over here. So KP and KI you can change from here and see the effect, right? So this is the basic simulation which I am showing over here. So you can simulate with different, you can say speeds. You can see the simulation is at 80 radians per second. I'm changing the speed to say maximum possible. Rated speed is 186. So let me keep it 140. So if I change the speed, motor should run at 140. If that is there, then I can say closed loop control is achieved. At running this speed, it should also produce the required torque. Over here, 200 Newton meter is the load which I have thrown on this motor. So that is the concept of the drive. You can see 140 it has reached and then it has stabilized. And also it is producing the required torque also. And at the same time, you can see the flux is rated flux, right? Now, let's see the effect of change in torque hysteresis band. So here the torque hysteresis, this was kept 0.05. Let me keep it 0.1. That is 10% variation on either side. So if I do it and once again simulate, we'll see the variation in torque is going to be more. So this part, when it stabilizes in steady state, the torque pulsations are going to be large if you increase it, right? So that is one thing which I wanted to show. Now, similarly, you can change the flux hysteresis band. You can also change the. Let me show you about KPKI. So you can see if I zoom this part. The set point is 140 and actual speed is 137.4, right? So you can say that much is the error. Now, suppose if I want to reduce this error, I need to increase the gain. So increasing gain is possible in DTC controller, in PI controller. I can increase. This is 100. Let me keep it KP2. I've increased double, that is 200. And let's see the effect. If I simulate once again, I have to allow the time to reach the steady state, and then only I can show you what is the effect. Okay, let's see. You can see the error has reduced. Now it is 138.7, right? Likewise, by changing the gain, I can reduce the error, but last gain also is going to affect the other parameters also. So this is an endless study, and the simulation also can be studied in wide different aspects. So this is a basic simulation where I have tried to explain how to do the fundamental skeleton of the DTC. What are the various parameters, basic calculation and basic simulation. We all are free to now work on it, learn on it, experiment on various parameters and learn a lot from it, right? That's all from my side in this video. We'll continue with more such videos in our next class. I hope you enjoyed and you learned a lot from this video. Thank you.